Testing, testing. Can everybody hear me okay? Okay. Hi, my name is Annie Gillum. I'm a senior at New Canaan High School, and I am a co-president of the Astrophysics Club. I've been volunteering here since last spring, and some of the things that we do with the Astrophysics Club are stargazing events, presentations in our planetarium, but what we've invested the most time in is our research on quantum dots. And this research I have led the past couple years, and I recently wrote a proposal on it and received a grant from NASA for it. So I'm going to talk about this a little bit. The title of it is The Effects of Ionizing UV Radiation on Zinc Oxide Quantum Dots Applied to Photography Film. So don't get lost yet. I'm going to explain that. Hold on. So as a little bit of an introduction on how I got into this, so the reason why we can just get by with sunscreen to protect us here on Earth is because we have an ozone layer, and the ozone particles absorb the sun's UV emissions, but up in space, astronauts don't have that ozone layer to protect them, and they're exposed to a lot of harmful ionizing radiation, such as X-rays, gamma rays, infrared, and ultraviolet wavelengths. So thinking of this problem, we started doing a little bit of research and found out that astronauts return with an increased risk for radiation sickness, cancer, diseases, and long-term central nervous system effects. And these health effects often go unnoticed with the high-quality space technology that we have today, but it's actually a really big risk for them to go up into space. And a fact about that is that 50 to 2,000 millisieverts that they are exposed to up in space is equivalent to 150 to 6,000 chest X-rays here on Earth, which is bad. So we have been investigating the idea of a super sunscreen and how we could potentially create like a powerful sunscreen to protect us up in space. So initially we began to research something called Cryptooctus neoformans yeast, which is a fungi that produces melanin. Although this is a bit of an outlandish idea, we were kind of thinking of the idea of how we can maybe artificially produce melanin that creates pigment in our skin as a sort of sunscreen. But eventually we did find out that this fungi was very highly poisonous and therefore pretty unfeasible for a high school club to be experimenting with. So then we started using quantum dots, which hopefully are not poisonous. We're not really sure, but we hope not. So the big question is, what are quantum dots? Basically, quantum dots are tiny crystals that are semiconductor materials, which means they conduct electricity. And what they do is they take in radiation and wavelengths such as UV radiation, and they actually convert it into visible wavelengths, which are more beneficial for us, like the visible light we see, like red through blue. And right now they're being used in TV screens, biomedical imaging, and solar cells, but they're still pretty underground, which is pretty cool to be researching them and like being like one of the first like groups to start working and trying to figure out what they can be applied to. So the purpose of using these quantum dots is to see how effective they would be in transforming harmful space radiation to beneficial energy, so kind of that idea of a super sunscreen again. Although we may not be able to completely coat like ourselves or space technology in them, as they are really expensive right now, eventually it could be an idea to look into or find something similar to that. So that's what we've been trying to research. So testing quantum dots on Earth is probably easier, but that wouldn't be very informative since we're trying to figure out if they would work outside of the ozone layer. So basically, we found a program called Cubes in Space that provided us with the opportunity to send our experiment up into space after we applied for it. And we would send it, we applied and were accepted after a couple of years, but up onto the sounding rocket. although I'd like to note that this is suborbital, although it doesn't completely go out of the ozone layer, it is still going to get us a pretty high exposure to UV, much more than we would get here on Earth. So it was a good opportunity to test the effectiveness of the quantum dots. And some of the applications that we were hoping to test are, like I said before, space technology and how they can protect organic life. But also here on Earth, maybe they could protect agricultural biotechnologies, biomedical healthcare engineering, and even power generation, as they are used in solar cells. So starting off with the materials that we use, I'm not going to get into depth with all of the experimentation, but I'm going to briefly explain some of the important materials that we used. So, of course, we bought quantum dots. We had funding from our school to find the cheapest quantum dots we could, which I'm not sure if they were completely the best quality, but that's what we could find. And the important thing is that their excitation level is 330 nanometers, which means that that's the wavelengths that they're going to take in, and then they're going to emit wavelengths at 530 nanometers, which is the blue wavelengths, which is the visible light that they're going to transform it into. So how are we going to actually test and measure how much visible light is being produced in this transformative process? Well, we started brainstorming and looked at the idea of photography film. So you know, in cameras, film paper produces pictures based off of the visible wavelengths onto it. So we looked into how we could use those as a way of measuring the visible light emitted from the quantum dots, and the solvent we used was dichloromethane. We also had a few restrictions from cubes in space, such as the size 64 centimeters cubed, had to be 64 grams, and it couldn't be in a liquid form, so we had to suspend it in epoxy resin. Basically, this involved a lot of engineering and trial and error on trying to fit it into this pretty small cube. You can see us holding it. It is extremely small. Good thing quantum dots are small as well. But you can see a little bit of our diagram on the setup of it. So basically we have a control side and a non-control side. So the control side just has epoxy resin with photography film, and the non-control side has the epoxy resin with the quantum dots, and that will let us compare, even if the results aren't completely exact with the quantum dots transformation, we can kind of compare the two sides to see the results. So we prepared it by creating the solution with the dichloromethane and the zinc oxide quantum dots. And another issue that we did find was we needed to figure out how we were going to make sure that only the visible light created from the quantum dots was showing up on the film. We didn't want any other light showing up on the film. So we had to create kind of like a dark mold. We used black opaque PETG filament. We 3D printed this with the control side and the non-control side so that we could block out all the excess light and try to create as much of a controlled system as possible. And we assembled the cube with all of these steps and put the film in a dark bathroom again to block out the excess light. And the way that we are planning to analyze the results of this is only a qualitative way at the moment, where we're just basically planning on looking at the photography paper and seeing if that blue color was printed onto it, onto the Kodak Gold film. But in the future, if we have more resources, we'd like to take a more quantitative result, where we take a spectrophotometer, which is actually something that it's a tool that it shines light onto the solution, and it gives you numerical data on the wavelengths produced. So that would give us more concrete data that we could analyze. And as to talk about the conclusions that we are hoping to make with the cubes in space process, we are hoping to just think about how space gear applications could be investigated. So if we see success with our results, we hope to make some conclusions and it will encourage us to do more research to see how quantum dots can be applied to space gear. And a few future changes, if we were to do this experiment again, was to use toluene instead of dichloromethane and an ultrasonic bath instead of just letting the solution dissolve on its own, as that would help the quantum dots dissolve a little bit more as they came in a solute form and weren't completely dissolved. So we need to dissolve them to make sure that their best qualities are showing. And I talked about this before, but also using a spectrophotometer would be the more quantitative way to record the data. We are planning to continue doing research with this because I talked about before, as I got a grant from NASA for our club. So that, and as well, we also applied recently to another program similar to Cubes in Space called TechRise that actually gives us funding as well. So these programs are going to help us continue our research process. And another issue that that I was unfortunate to hear this summer was that FedEx actually sent our experiment to the wrong place. So after all of that time and process of putting this together, it actually didn't make it up on to the sounding rocket, but we're scientists and we don't give up. So I spent a lot of time on the phone with FedEx, and eventually we got our cube back and we're able to send it back out to Cubes in Space's other program, which is a hot air balloon. Although this isn't going to be exposed to as much UV radiation as it doesn't go as high, it is going to be exposed to UV radiation for a longer period of time, allowing us to get hopefully some pretty good results in the meantime as we prepare to continue our research. Before I go into some current events that I'm going to talk about, does anybody have any questions, or you can come up to me after about the quantum dot research? I hope I explained that well, sorry. Okay, I'm just going to talk about some current space news that is pretty exciting. So recently, this was a couple days ago, November 4th, there were some studies released about a fast-feeding black hole. And basically, this is NASA's James Webb Space Telescope and the Chandra X-ray Observatory are two powerful telescopes that have helped scientists discover a supermassive black hole called LID 568. And this black hole was found just 15 million years after the Big Bang, which is very early in the universe's history. So what makes this supermassive black hole special? Well, the black hole is eating matter at a rate 40 times faster than what we thought was possible. So originally, scientists have theorized with the Eddington limit, which is the process of gravity pulling in, but at the same time pushing pressure out, and they thought there was a limit to that process happening. But this supermassive black hole was happening 40 times faster, which is much faster than expected and kind of defies that physical theoretical proposition. So the James Webb Space Telescope detects infrared light from the black hole and its surroundings, and the Chandra X-ray Observatory picks up X-ray emissions, which is how they were able to observe this. What's happening around the black hole is basically the James Webb Space Telescope is seeing a really powerful Gauss outflow, which is much greater than that pressure out compared to that gravity in, that rate that they expected. And this is part of the process called accretion, which is where the black hole pulls matter in, grows, and then shoots out energy. So why is this finding important? The LID 568 tells us how supermassive black holes might have been formed so quickly after the Big Bang, and it's consuming matter much faster than expected, helping scientists understand how these giant black holes grew in such a short time. So although they don't completely know too much about it yet, it is a pretty groundbreaking discovery that is going to lead us to make some new conclusions about black holes, and also the cosmology of our universe, the time period. And so another recent event from October 18th is the discovery of axions, which is a hypothetical particle, so we don't actually know that it's a particle yet. But a team of scientists found axions around a neutron star. So neutron stars are basically stars that have died after gravity pulling them in and they collapsed as in a supernova explosion. And axions are special because they don't glow, reflect, or absorb light that we can see. That's why they're really hard to detect. So does anybody know what this process is similar to? It's basically similar to the idea of dark matter, which is a pretty cool idea that a lot of scientists don't know about. But dark matter, same thing. It can't be observed, which is why it's like a pretty mysterious idea. But it's about like more than 80% of our universe. So the matter we know and see is only like a very, very small sliver. So the idea that axions could be discovered and could be connected to dark matter is pretty important. And even though axions aren't visible, we can spot them by how they interact with other particles, especially when they're near magnetic fields, so we can observe their gravitational interactions. And these interactions might create a sort of hazy cloud of axions around the neutron stars, which makes it easier for scientists to detect. And then a few more things upcoming in astronomy is there's the Northern Taurids meteor shower, November 11th and 12th. NASA's Artemis mission 1 mission in 2024, where astronauts are going to return to the moon for the first time in over 50 years to take some data and see if that could potentially be a place to inhabit. And NASA's Europa Clipper mission took off on October 14th, 2024, and the purpose is to explore one of Jupiter's moons, Europa, which scientists have been tracking, and it could be a potential spot for our inhabitation in the future. Any questions as of now? If you guys have any questions too, like about this or about the research, please come up after. Okay, and then I'd like to also thank all of my friends and family for coming. It means a lot to me that you guys all made the trip up. Thank you. Thank you. Okay, that's it. Thank you.
Very nice.
Thank you.
You've done a lot of work. I just want to say, I was an airline pilot for 32 years, but on the transatlantic routes, they're high altitude, high latitude. So I've got statistically twice the chance of getting melanoma than a regular citizen because of ionizing radiation that goes right through the arena and zaps you. So even if you can't get suborbital flights, balloons get up pretty high, and they get up plenty high enough to get a very good increase in altitude.
That's actually fun. Yeah.
So yeah, you've got